Okay. So I thought I'd start with a brief introduction of what a free electron laser is, since we have NSLs here, NSL2 here, so you know about storage rings, so I want to make a contrast. And I talked to you a little bit about LCLS, the Linac Coherent Light Source, the SLAC, how they came about, and what we have learned so far the last 5 years. And then I'll talk briefly about LCLS2 project, the upgrade, follow up on LCLS. And then I'll sprinkle along the talk some thoughts about the challenges that we face as facility managers, laboratory managers, and as a community. So before I go, I want to thank the team here. I tried to acknowledge everybody in the slide, but I want to make sure I do it before I forget. So a synchrotron, a third-generation storage ring, NSL2 type machines, you have ondulators, which is magnetic structure that wiggles the electron beam around, and it generates very intense X-rays. But here, intensity is proportional to the number of electrons in the bunch, because they emit incoherently. If you go to a free electron laser, the feedback between the X-ray generated by the undulator to the electron beam itself eventually orders the electron beam into a microstructure. And now the whole thing radiates in phase. So you got n squared gain. Right? That n is a big number, on the order of 10 to the 9, 10 to the 10. Right? So there's one of these holy grails that people want to do for a long time. I think it started off in the 70s at Stanford, and then a lot of work actually done at Brookhaven. Claudio Pellegrini and company extrapolated from infrared to X-ray. And serious work being done at ATF, demonstrated first, and then SDL. Right? So there's a lot of work being done at Brookhaven. Without those, LCLS would not have been possible. So now, to summarize the differences of an FEL and the storage ring. So one thing is this 9, 10 orders of magnitude more X-rays. Right? So if you don't remember anything after the talk, I think this you need to remember. Is a free electron laser give you gauds and gauds more of X-rays, 10 orders of magnitude more, in fact, compared to a storage ring in a single bunch. It comes in very short time, because the nature of how to generate the FEL source, you need to have very high P current, which means these things are naturally very short. And the third thing is something called seeding, which I'll come back, is the energy bandwidth of the free electron laser is narrow compared to a storage ring. The typical storage ring out of undulator, you have a bandwidth about 100 electron volt. In FEL, you can get down to 1 electron volt or less. Right? So these are the things that, if you remember, is FEL gave you lots of X-rays. It comes in very short time, on the order of femtosecond, and it gives you the energy you want. Right? There's no waste. You want to do experiment with the one energy, all the X-rays are in that bandwidth you want. And one other thing is X-rays are coherent, which means all the photons are actually in phase. Right? I'll come back to that. Right? So if you remember, these are the property of a free electron laser. So now comes, okay, this is nice and fine, right? How do we do it? What you need, come back. So what will you do with a source like this, right? So this is a old picture. There was a bet between Senator Stanford and Edward Milbridge about whether when the horse galloping are the 4 hoops off the ground at the same time or not. Right? So this is actually was an experiment done at Stanford land. They have these trip wires setting off the camera. So as the horse running across the trip wires, they have these steel frames, and eventually they make a movie out of this. So now, FEL, when we think about it, right, like I said, it's a very short time pulse on the order of femtosecond. That means that's the time frame between vibrational of 2 atoms. right? So in principle, then you could take a movie of this, but a movie of a chemical reaction when the bond's being made or broken, right? So this is something that I'll come back to, right? So this is a great idea, right? But how do we do it? So this is a cartoon. To do this, you have to start off with a very bright electron beam. And that electron beam will be generated by sending a laser onto a target, generate electrons. Electrons then get accelerated to very high energy. So they need a very long linear accelerator. And then you go into the undulator, like I was trying to show you before. The X-ray generated from the electrons in undulator feedback on the self. You start seeing these bunchings of electrons. Yeah, here comes the undulator. You start seeing the electron bunches generating X-rays. X-ray then feedback to the electron bunch itself, and then orders into these micro bunches. And so the undulator needs to be very long, on order about 100 meter long. And at the end, you generate the free electron laser, and then you have to dump the electron beam. So let me go back one step. So at the time when people thinking about how to build this, we didn't have the gun. We didn't have a high brightness gun. A lot of that gun development actually was done at ATF here. We didn't have the Linac, certainly not here. And also the undulator is 100 meter long, so very hard to do. Right? So here comes SLAC. Right? SLAC at the time, high energy physics program already stopped. So needing a new mission, what to do next for the laboratory. So the lab was built, the first director of laboratory, Pete Panofsky, when people asked him in 1962, when the laboratory was first built, this 2-mile Linac, people asked Pete, says, how long do you think the laboratory will last? Pete says, about 10 years. If we don't have a new idea every 10 years, then we don't deserve to be here. Right? So the laboratory is going through several of these transformations. The last one, the latest one, is this one, is taking the Linac, the idea of X-ray free electron laser, says, why don't we try to experiment here? Right? And so the idea is then take the Linac, the last third of it, and use the infrastructure you already have, and build a tunnel through here, and build the experiment behind here. Right? And it also takes Department of Energy, the vision of the Department of Energy, to do the experiment with SLAC, right? Because that was $400 million experiment. And people didn't know this will work. Right? Although there's a hint of all the pieces are being developed. Right? So it was a very bold move from the basic energy sciences to DOE to take that gamble as SLAC. And so the plan was to take the last third of the Linac, build a high brightness injector, build undulator hall, and end station. And these are 6 stations. And another thing very different between the FER and the storage ring is there's one undulator, so only one station gets to use the beam at any given time. So the number of experiments per year will be very small. And the cost of operating this is very high. Right? So we have to figure out a way how to do the most impact for science, almost like the high energy physicist days, that you have a big machine only do a few experiments. So then, in terms of the science case, right? So this was considered as an experiment, and so how do we build a scientific case for something like this, right? So there was many workshops, but in the end, I think that this is experiment that caught people's attention. Imagine you can drop a protein into the X-ray beam, and X-ray beam will scatter from the protein, create this speckle pattern in the back, and you accumulate many of them. Eventually, you can reconstruct the structure of the protein, right? So at the time when people proposed this, I think there were a lot of people doubting this ever going to happen or not. So I think these big projects always have something extremely hard in front of it. Whether you can do or not doesn't really matter, actually. It's something daring in front of you. Right? I think I remember Steve, NSL2, when we started, we said we need to do a nanometer focusing. At the time, most of the people said, you're crazy, you'll never be able to do it. Right? So Steve gave me a tour today and telling me the optics R&D now is getting 10 now. Right? There's no showstopper to continue to improve. These are the things that drives the community, the best people, to work on new ideas. Right? So I'll come back to tell you where we are now. And so 5 years ago, April 2009, John Galida in the center of the picture, also from Brookhaven and SLS. So they turned on the machine, and it worked. Within hours, FEL worked. Right? It was a big surprise to everybody, but it shouldn't be, because there had been accelerator physicists, engineers at SLAC, been working on that Linac for decades. Right? It is because a lot of these people, they know every single detail of the Linac. That's why it worked. It's not because of dumb luck. Right? It's a very good people working on something for a long time. Right? So a lesson for me actually is critically important. Laboratory like ours be able to keep and develop people for decades, because there's nowhere else you have people like this. So with that, it's the first step. Then there's a series of R&D program in the last few years to address the thing I told you about. Lots of X-rays. How many do we actually have? Can we get more? How short is the bunch? Can we find a way to measure it? It's actually very hard, right? Think about it. How do you measure a femtosecond X-ray pulse? And then how do we get the energy all into the right energy within the bandwidth you're interested in? Right? So these are the things. There's a very aggressive R&D program was put together, and these are the results. So first, it's the diagnostic was developed to measure the length of the FEL pulse. So this is annulator generating the free electron laser beam, and then you apply a electric field so that you can spread the electron with different energies in space, and then you have put them into a bending magnet, spread them out even more, and you're imaging it. So with that, this is, if you don't do anything, the electron beam looks like this. This is time and phase space in some ways. If you turn on FEL, you see electron lose energy into the X-ray beam. So you can see clear signature of the electron beam. So with that, we can now learn how to operate the free electron laser better, right? So this is the shortest bunch we ever able to measure now. It's 2.5 femtosecond, right? So there's a program now. See, can we improve the sensitivity so we can eventually produce and measure sub-femtosecond X-rays? The other thing is interesting here. If you look at this piece, there's a double horn, right? That means the electron bunch actually generating X-ray both on the front and the back ends. So it's probably not the best way. So you really want to do is put them all into similar like this, right? Move these two peaks into a single peak. You have more intensity in the right place, right? With that tool now, that's exactly what they did. You can remember this double horn structure now become a single piece, and intensity went up, right? So this is getting close to the highest P power generated at LCLS. So it has about 0.3 terawatt. So converting to numbers for the experimentalists in the room, that's 10 to the 12, few times the 10 to the 12 X-rays per bunch. And that's about 1 second of all the X-rays coming from a synchrotron. Right? So the P power is high enough now you can start doing single shot experiment that you have enough signal above background for those type of experiments. And that we are continuing to look for ways to improve this. One thing is because the X-rays generated from the resonant condition for the experts in the room, that if you follow that by tapering the undulated gap at the very end of the FEL, you can continue to keep that condition and putting more and more energy from the electron beam into the X-rays. And that concept, again, was demonstrated at Brookhaven. We actually are using that now. The third part is, remember the X-ray was generated first by a seed of electron beam in the undulator. And that seed is a noise, get amplified. So the spectrum, if you measure the energy spectrum out of the FEL, this is what you get. Around 20 EVs. So every pulse, they come in and jumping around. Okay. So it was a great idea actually here by Li Yu to see the FEL with laser external seed. So you get the harmonics out of that. Then you have a transform limited output. And that concept is difficult to get to very hard X-rays, but we are continuing to pursue that. In the meantime, in Hamburg, there is a proposal to do what we call the self-seeding. Instead of an external seed, you would take first half of the undulator, generating something on the order of a gigawatt, and then you take the X-ray out, you separate the electron beam, and you recombine them again, so that you're essentially taking out one sliver of this bin here and amplify that piece. Right? If you do that, what you did is basically compress everything into a single spot. Right? So now you get about 10 to the minus 5, few times 10 to the minus 5 bandwidth, which is typically what you have to do by putting a monochromator in the synchrotrons. Right? So this is give you a way to give you the energy you want without having to monochromatize the beam and throw away a lot of X-rays. So this is for AKEV, and we recently have demonstrated that for soft X-ray now. So for the experts in the field, this is almost a single mole, only a few moles in that peak. And so there's in the parallel, there's a very large effort in developing the detector for a free electron laser. It needs an imaging detector which can read out at the repetition rate of the Linac, which is 120 hertz. Right? So imagine this is a few megapixel detector, about 2.3 megapixel detector, running at 120 hertz. The data rate that you get is a tremendous amount of data you get. Right? So I won't have time to go into that. So there's a huge amount of effort now putting into this to handle the amount of data you get and how you get the most information out of the data you generated. So let me actually come back to science now. So the next series of slides, I'll give you a few examples of what's been done now. So one class of problem is photochemistry. Like I was saying, if you have a femtosecond probe, you should be able to make a movie of how you make and break a chemical bond, right? So vitamin D, like we all have, You get more if you go out in the sun more, right? So it's a UV light that going through your skin that actually generating vitamin D3. Okay, so the prototype molecule try to understand this is the hexadiene, cyclohexadiene. Right, so the idea is, can we learn by UV photoexciting the molecule and understand how the molecule evolved eventually into something like this, right? It's actually scientifically very important because for most of the people in chemistry or physics, you will know that the electronic calculation, structure calculation that we do, you usually assume the nucleus, the nucleus atom actually fixed, right? That's the starting point for you to calculate the electronic structure. But when you break a chemical bond, the nucleus actually moving at the same time, right? So that's a theoretical challenge for chemists in particular. So the idea then is if we can give you the movie of how the atoms moves, there's another piece of information for the theories to improve the understanding that we have. And so the experiment is set up in such a way, you will see a lot of that now, is you have X-ray pulse coming in, you have a laser that pumps the system, and you can then adjust the time delay between them, right? Like stroboscopically, you can change the time delay. So you have a starting point always with this pump, right? X-ray laser come at different time delay. That's how you make a movie. And then you have the imaging detector I showed you before to capture the scattering intensity. So this is the raw data you have. It's about 1%, the changes that you see here is about 1% of the intensity that you measured. So it's not bad. And we don't quite go far out enough in momentum transfer to get very high spatial resolution at this point yet. But in time, I think we will get there. The reason this experiment is very hard is because for a long time, these experiments were done by electron scattering. Because this is a gas phase, so the concentration is very low. And without the 10 to the 12 X-ray per bunch, there's no hope to actually see any signal above the background. So this is the first time we're able to see it. And so this is the molecule. And based on the scattering data I showed you in the previous slide, this is the best fit of how the molecule was excited by a UV light, and the carbon bond stretched out, broken, and then they arrange itself, eventually get to the state, final state. So this is the first time now we can provide a real-time movie like this for how to make or break a chemical bond. The next set of examples is more material science. So similarly, if you put a laser pumping a piece of metal, for example, you create a shock wave in the material, and the lattice expand. And if you can take snapshot of that, you can understand the strain rate of the material, right? This is something that real-world material scientists are very interested in. So this is the first demonstration of that. It's a fairly high power laser. Focus onto the specimen here is a piece of copper, and you're looking at is the diffraction rate from copper from the lattice. And every shot, you basically destroy the sample. You have to move to the next piece. Now, if you do that and you accumulate at different time, you will see the diffraction ring get developed. You see the breakup. So from that, you can then analyze the strain rate of the material. So after this paper was published, Rolls-Royce came to laboratory and says, we're actually interested in this. We actually don't know how they found out these experiments. So they're interested in the fun, right? You have these turbine blades. They're spinning under a rate extremely high, right? So they have this specialized alloy that they have. They understand how these alloy behave under these conditions. So these are the specimens that they brought to LCLS. And so this is a single crystal, right? You see at the moment, right now, these are very dim individual spots. These are from single crystal diffractions. Once the laser hits it, it breaks into domains. So you see a diffraction ring come out of that. So left-hand side is reference. The right-hand side is once it's shocked. You see that start to happen now. So they have models. They have very sophisticated computer models of how these things work. So they use the data that they took at LCLS now to confirm the model that they have. Another set of example is the following. So this is another experiment. Uses the coherent property of the X-rays. When the X-ray is coherent, means that the scattering from, this is a gold nano crystal, the scattering from front to the back all interferes instead of scattered independently. So the interference means that if you have the thickness of one facet, will give you the interference pattern, give you one of these rings, these stripes, right? So you get enough of it, you have a three-dimensional picture of the object. This is an experiment first, again, demonstrated at Brookhaven, actually NSLS. Janusz Kurtz's group, John Mel, as it was a student doing his thesis. First time they demonstrated they can use coherent X-ray imaging a non-periodic object. So that field is picking up, in particular for high brightness source at NSLS2 and free electron laser like LCLS. So in addition to having the image, if you use laser to excite the nanocrystal, what happens is you have phonon get propagated, right? So the laser heats it up, so the lattice stop to move. Phonon means the atoms are moving on some time scales. So that gives you the scattering differences in the scattering in the phase of the scattering. So you can register that in the diffraction data too. So from that, then you can using different time delay to find out the strain within the nanocrystal in time. Right? That tells you how the energy propagating throughout the crystal. Right? The first time we were able to see something like that. And this actually got attention of another group of people which we never thought would come to use LCLS. So these are the people interested in superfluidity in liquid helium. Liquid helium is a quantum system, has vortices and all that. The problem is helium is very low Z. X-ray scattering, you basically see nothing, right? So somebody got clever, realized they can decorate the helium bubble with the xenon. So you have something which is heavy embedded in each of these bubble there, right? So the same thing I showed you before. You can see the shape of the droplet. You can also see the arrangement of the droplet, right? So that gives you the vortices, the diffraction pattern from vortices, and tell you the arrangement there, right? So I think there will be a lot of new things that we have not thought about how to use this source for. This is not trying to do something like I was trying to tell the other example of time-dependent phenomenon. This is not. This is static, right? But there are a lot of very interesting things one might do with this very high-intensity X-ray beam, even the static problem you try to understand. So come back to another set of example is in structural biology. Remember when I started, the thing got everybody's attention was, see, can we really do single molecule imaging, right? So this is give you sort of where we are now, right? I don't need to tell this audience why X-ray is important for structural biology. Basically, every 3 years, you will have Nobel Prize coming out of using the synchrotrons, right? The difficulty is, as the problem getting harder, is the object you try to analyze are bigger and the harder to crystallize, right? So in LCLS, what people are trying to do is you have a jet, you would drop the crystals down, and then you try to hit it with X-rays. So this is hit and miss, right? At the beginning, the hit rate is quite low. In fact, a lot of people try to figure out how to improve that. I think a lot of people here too. Alan Orville actually has this ultrasonic thing to create bubbles and have crystals sitting in the bubbles so that you can increase your hit rate. Because the crystal, most of these things are very rare. You don't have a lot of samples to do these experiments if you waste a lot of them. So again, what happened is you drop it down, X-ray hits it, you record the image, you do 1 million of these things, eventually you can reconstruct a 3-dimensional image. This is not a single molecule, this is still a crystal. But the crystal can be a lot smaller than the crystal you use today in the synchrotrons. And the other thing that we demonstrated is actually proof that you can do room temperature. So you can actually destroy a crystal at room temperature without having to freeze it. Right? Most of the experiments you see in the synchrotron, crystals frozen. Right? So you always have this lingering doubt whether that's a natural environment or not. Right? So now we can do experiment in room temperature in the natural environment of the protein. So this is the case where there's a bacteria. It actually grows the crystal inside. And so you can drop this thing down, and then you can kill it and get diffraction data, eventually get a structure out of it. So this is one of the first structures solved, unknown structure solved. Right? So these give you a very high resolution structure with APL. So now this become quite routine now. The other thing people are working on now is use of a free electron laser generate 2 different energy at the same time. So I won't go into the detail, but we can do it now. So you can have a single bunch coming out with 2 different energy varied by 50, 60 electron volt in very close time. So that for crystallographers in the room, that gives you a way for phasing. You can collect diffraction data from 2 different energies at the same time. Right? So this is a very important step. I think we are getting there. The other thing being done a lot by lots of people is to improve the injector so you can increase the hit rate, like I said before. So this is basically like a toothpaste. This is lipid cubic phase crystals that they're coming down very viscous, coming down slowly, so you can hit them almost by choice. So this is being done now by, actually, Brian Kobilka sits here. Brian is the one who won Nobel Prize a few years ago for solving the structure of GPCR, and he has a drawer full of crystal with low resolution, and the hope is LCLS will be able to take them to higher spatial structure data. So right now, in the synchrotron, what they can get is between 2.9 to 3. Now, we can go back by a half an angstrom resolution. Now, this is very important because until you get to below 3 angstroms, the structure is not good enough, accuracy is not actually call it the structure soft. So going from this step to this step consistently is going to be very, very important. Right? So this is a project Alan is involved too. We're building a new station. Actually, so this is a way, instead of using the liquid jets, this is actually putting on the traditional goniometer that you see in the synchrotrons. You basically move these things quickly, right? So these are coming. So on the imaging side of a individual particle, so Janusz Haidu's group from Sweden has been working on big things and try to get to smaller things, right? So we approach this from two sides. One side is from the crystal, getting smaller and smaller. The other side is we're coming from the individual particles and get that to smaller too. So in this case, it's a cell. You drop it down, and then you do the image. So at the moment, they get about 100 nanometer resolution. It's not so impressive, mainly because the wavelength they're using. Right? So this can be significantly better once they go to high energies. So in this case, you can start seeing some internal structure of organelles inside the cell. They now start trying individual particle now. So the way they're doing it is they decorated this with gold. Remember the experiment in helium, you decorate it with something heavy, you have more scattering power for the object. So they have tried some of these things now. So with these experiments now we know, in order to do single particle imaging, single protein imaging, we need a factor 10 more in the number of X-ray we can pack into a single bunch. Okay. Then we need to focus these things down to 10 nanometer sort of spot size, right? So the optics being developed in SLS too, and elsewhere. Between that and what we're doing now, continue to improve the way we can generating higher P power from FEL. I think we might get there someday. It will be quite a bit of way to go, but we know where we are. How far do we have to go? Right. Now, the last set of slides I'll show you is a new area of science which is created because LCLS. The thing that I've told you before, chemistry, material science, biology, which you see a lot in the synchrotrons. So this is something completely different. This is what we call the high energy density science. So if you look at this is temperature and density, or the other way look at this is pressure, right? So we down the bottom here, up here are these relativistic plasmas that use in fusion. So these are the things that we try to understand. These could be the future source of particle beams, right? So there's a big experiment called Bella at Berkeley using laser as a driver to generate the future accelerator source. These are the things that are relevant to gamma ray coming out of space. These are the things that has to do with fusion in inertial confinement fusion in Livermore. And these can also be a bridge between static high pressure experiment being done in synchrotrons. If you want to go to 10 megabar and more, you will not be able to do it with static in the synchrotron, but you can imagine have a long pulse X-ray slowly ramp up the pressure. Right? So these are the things that we are pursuing now in the new station that we have. And so with that sort of between these four sets of examples I give it to you, I hope you get a sense of where LCLS is now and where we're heading. Now I'll skip the rest of these few slides. I'll show you LCLS 2. So last February, there was a Basic Energy Science Advisory Committee meeting to review all the existing facilities. Steve and I both gave a presentation of facility that we have, our plans are. July, there was another Basic Energy Advisory Committee meetings. That meeting asked for the future. So what we intend to do for all the labs. So SLAC went in there. We're looking at what we have. We realized the capacity is not there. We really need to increase that. So the proposal we put in was dig a second tunnel, and we will have 4 independent stations instead of 1 at the moment. And the energy, we need to expand the energy rich to higher energy so that we can go to a higher structure data. So LBNL put in the high rep rate FEL proposal. And then the outcome of the Basic Energy Science Advisory Committee meeting was basically try to combine these two, ask for a design that can generating high rep rate and X-rays. The Berkeley proposal was limited to soft X-rays. So the spec out of the Basic Energy Science Advisory Committee is high rep rate, but cover a much bigger range. So we went back, modify the LCLS2 proposal, using the first kilometer Linac as SLAC. We'll take out the copper Linac and put in a superconducting Linac in its place. So what it does is the conventional Linac we have, you can up running to 120 hertz, 120 pulses per second. With the superconducting Linac now, we can run this up to 1 million pulses per second, right? So there's a lot of experiments currently are not feasible, will become feasible now, right? So it's a huge step for those who know about SLAC. Going into superconducting was not an easy thing for most of the people to swallow. So, but anyway, so that started last fall. We put together a multi-laboratory collaboration. Fermilab and Jefferson Lab have a lot of history with investment from high energy physics DOE and nuclear physics DOE to develop the superconducting technology that we can use. And we have Berkeley, Oregon involved in building the undulators, and Cornell doing R&D on the cavity and also on the injector. So the collaborations work extremely well. The project now has passed critical decision 1 last August. We're working towards critical decision 2 and 3 next year. The schedule is extremely aggressive. I'll come back to that, give you the reason why. And so it's doing quite well at the moment. So it will give us much extended energy range. It's a complicated slide, but what you need to remember is we right now are limited about 10 keV. The upgrade will get us up to at least 25 keV. I think we can go even more than that. The high rep rate, the superconducting Linac will go to 5 keV. There's enough room in the Linac to continue to add in the future that we can increase that energy even more. And the laboratory is going through a long-range planning. So this is what we have for LCLS and LCLS2. There are enough real estate around it to continue to build up in the future. So let me close by showing this slide. This is a slide that Persis Drill, my predecessor at SLAC, and Jim Murphy made for Basic Energy Science Advisory Committee before the last July meeting that recommending the new FEL specification. Right? The world has changed. Right? United States after World War II is the dominant power. We made most investment in science. Now Europe, Asia are making a lot of investment in science. So that's one thing. And the other thing is the cost of these things are going up. right? These are billion-dollar scale. Every big machine that we're talking about is $1 billion. Takes a long time to build. So how do we, as a community, as the laboratory, as a system, find ways to be able to keep the competitiveness of the country at one hand, and how to best use the resources that we have, right? It's a challenge for doing me as a lab director, but everybody else in the room too, right? Is how do we do the most impact for science, the shortest possible time, right? So I'll leave that for you to also think about it as well, right? So let me finally close with this. I hope you come visit me. If you come to my office, this is the picture that I see every day. This is the picture before I left, it was a picnic. So when I kind of get sick and tired of what I do, I stand in front of the picture, try to look at some of your faces. Thank you. Oh, it's 5 o'clock. Perfect. Between me and the wine.
Are there questions?
Sam? Oh.
Aren't you in danger of stimulating more demand than you can meet? LCLS, LCLS?
Yes.
So what does the field do about that?
I think we have to rethink about how we do things. LCLS right now, every experiment, on average, there are 15 people. Okay? Now, the first 2 years, most of the approved proposal actually went to Europe. Because Max Planck institutes and all these large labs in Europe are much better prepared than we do. They'll have a big team. They come prepared. They have the sample done right. They bring their own instruments sometimes. They have the theory support behind them. And the funding that we have, the group are too small. Right? So one way I think is build much bigger team so that you have specialization of things so that the impact of every beam time, it's hard to increase the beam time, right? But you could increase the impact. Okay? That's something I think LCLS is probably the most extreme case. Right? Steve and I were talking this morning about NSL2. Even NSL2, I think is heading that direction too, because the instruments are very sophisticated. The throughputs need to go up. So unless you have all the tools before and after, they're not going to optimize the input, the impact. Right? So I think it's a fundamental shift of how we do science and how we fund science. Because the way we do science is driven by how funding is coming from, right? So we have quite a bit of discussion with BS of can we fund these block grants, right, like EFRCs. EFRCs, the Energy Frontier Research Center scale size grants, right? So those are $2 to $4 million a year for five years. So you can have a large collaboration of people working on a problem that's significant. So that's one way to address it.
Nick? Peter, sorry.
When does the DAISY come out?
The DAISY X-FEL, I think, scheduled to come out in 2016, the end of 16. So the differences between LCLS2 and X-FEL is this. X-FEL has this 10 hertz macro bunch and 27 kilohertz micro bunches within those 10 hertz, right? It's very difficult to build optics for it because the heat accumulating on the speed very quickly. And the detector, you have to read out at that speed, right? So LCLS2 is a truly CW. So it's equally spaced megahertz. So I believe there is intrinsic advantage of a CW machine compared to a pulse source like XFEL. If you talk to them, they may not agree with what I'm saying here, right?
It's a fully superconducting machine. Why couldn't it do what you're doing?
They could, but they will have to reconfigure things. In fact, they have a team of people to study how they can convert that into CW, right? So they will drop the energy from current energy to about 7 GeV, right? So they're studying it now. It would, but then a lot of investment they already made that they will have to reinvest again, right? I think you probably one of those people recommended to them early on go to full CW. They didn't do it, right? So the urgency actually, Alpha Science recognize the technical differences between this and that. So they push really hard, ask SLAC to move on this one more.
You gave some really elegant examples of how you can use the 2 femtosecond pulses or 1 femtosecond pulses to resolve some of the chemical dynamics and molecular motions. One of the interesting time-resolved aspects is doing electron dynamics, where you have things like electron fertilization, et cetera, where you have to get to shorter durations. It's interesting. So the question I have is, there seem to be two paths that you potentially have to get into attosecond. You have 20 volts of bandwidth in the SASE. If you can make that coherent by injecting a chirp pulse or something that can compensate the dispersion, you might be able to, you have the bandwidth to get to 50 attosecond pulses. And the other thing is, as you mentioned at the very beginning, you've got lots and lots of photons, you've got short pulse, your intensity is very high, there are nonlinear susceptibilities, and the nonlinear conversion could also lead to a pulse shortening. I'm sort of wondering, is going toward attosecond anywhere on your radar?
It is, right? Exactly the approach that you suggested, right? So I think coming back to the other point I was trying to make is how do you make $1 billion project, a very large thing, move quickly, right? So these R&D, these new ideas, need to get pursued at the same time, so that every 6 months you actually have something new. It's not sitting there and says, I have this thing, I'm going to just, crank it, right? You have to always do something new. Right? And that has to do with how you would allocate your resources between what you operate things versus how much you do your R&D on. Right? I think these are the hard decisions. I mean, Steve, right, will have to make all the time. What's the right balance of providing more support you get more user through versus R&D that you're generating a new idea for the next step. I think we kind of tilted more to the user support side more than we should have, because my experience at LCLS, for example, is the staff are not getting enough time for the research. So we need to find another way to do it. But coming back to, if you have a community, right? So if you carry the community with you, then you're not doing this all by yourself. It's the community can actually do the R&D also, right?
We have time for about one more question. Let's thank Chi-Chang again.